Hi, everyone. So today, what we're going to do is I'm just going to tell you what's on the test. It's pretty obvious because this is our first test. The second test, this might be a bit more important to do a summary because they're not exactly cumulative. They each test emphasizes something, but there is a bit of a overlap. So let me just see how many people are here. Looks like there's six people. Also, maybe I should have mentioned earlier that you should be available for during the week of the test to be available during the other class during the regular class times because that's when I'll do live streams. And this is your opportunity to ask me questions. So don't be afraid to ask in the chat. Do I need to know something or whatever questions you might have? And the only other thing I should mention is due to a problem with scheduling, I have medical tests that I have to go to this Wednesday, and there's you can't schedule it. You have to go by their schedule. You can't say to them, "Well, I've got these other duties." They're completely um, uh, insensitive to that. So I apologize, but at some time on Wednesday I will be around. I will be available. I'll just email, and then I can even do like a 2-3 hour live stream where people can just jump in and jump out at any time they want and ask questions. The test will be on Friday, and its format will be the same as the assignments. Oh, okay, I think that's enough to logistics. So what's on it? What are the topics that are on it? And I've got them listed here. The first topic that I gave you guys was measurement and unit conversion. Okay, and I'm going to go through the topics first, and if you want me to do questions on each, I'll do them. Otherwise, I'll pick one and maybe do that for the remainder of the time. But I really don't want to do a question on unit conversion. It's really simple. Still, you have to start somewhere in the course, and measurement is a good place to start because physics is a science, and measurement is part of a science. The only thing don't forget is that the MKS. I mean, you know the metric system, but there are particular units that we're going to use as our base unit, okay? And for time, it's the second. For length, it's the meter. And for mass, it's the kilogram, okay? And we haven't used mass yet. That's going to be right after the test, but it's the kilogram, not the gram, which is a typical mistake that's made there. Okay, so the first major topic that we looked at was general 1D kinematic. The word general means that all possible motion a mathematical description of all possible motion in 1D. Okay, and this is actually the question that I would like to do if there's no other, if you guys have no preferences at all. Okay, and that means I give you some arbitrary function of like how something moves in 1D, and you should be able to answer all kinematic questions about it, such as like what's the velocity, what's the acceleration, what's the average acceleration during some time intervals, things like that. Okay, and so that's one general 1D kinematics. It requires calculus, and so I'm not going to throw functions at you that are hard to differentiate, but you should be able to differentiate polynomials. Okay, and then we looked at a specific case of 1D kinematics. So this is the general case. The specific case was constant acceleration. That's like falling, or situations where like you're braking at a common speed. And the equations you need there, the equations that I derived for you there, are that the position is equal to 1/2 the acceleration t squared plus v naught t plus x naught. V is equal to at plus v naught, and v squared is equal to v naught squared plus 2ax minus x naught. Okay, so that's that, and they're fairly simple questions to answer. The 2D kinematics incorporates these, so if you have a question on 1D kinematics, I'd rather do it in the context of 2D kinematics because it incorporates all of the 1D constant acceleration stuff. Let me see if there's any questions in the chat. Nope, no questions yet. Let me continue. Just type in at any time because um, I only can check periodically. Okay, so another thing in 1D that we did was the harmonic oscillator. Now I did do a lot of calculus in that presentation, but I'm not going to expect you to reproduce it. But don't throw it away because it reappears later in the course. Okay, and at other points I will be testing you on it, especially next semester with waves. But at this point, we're just starting up, so I just did 1D kinematics. So we're just doing the results of the uh, of the analysis, and there are a few equations that come out here that you should know. Yeah, and that is that the angular frequency is equal to 2 pi over capital T. T is the period. So 1D harmonic oscillation, something is oscillating back and forth like this. Okay, it has a period of oscillation, which means that if you start at a particular point of the cycle, say it with the one extreme at one end, it'll go to the one side and back in some time t. That's called the period, and it's given the symbol capital T. There it is right there. But capital T, you could rewrite these equations in terms of capital T, but they're more interesting in terms of this omega, which appears over and over and over again. And so omega is equal to 2 pi over capital T is the angular frequency. You don't actually measure it in the lab. You measure T in the lab, but omega is still it's useful in the equations. Okay, then as the thing oscillates back and forth, the velocity changes over time. Okay, and the velocity is zero at the endpoints because it has to stop at the endpoints, and it's fastest through the middle. That's called Vmax, and Vmax is equal to omega times a, the amplitude, and the amplitude is the maximum displacement from equilibrium. If this is equilibrium and it oscillates back and forth on both sides of equilibrium, it travels a certain distance on one side, it travels the same distance on the other side. That maximum distance that it travels, that's known as the amplitude. So the maximum velocity is related to the amplitude. Okay, and omega is the factor in there. So Vmax is equal to omega a. And then Amax, which is the maximum acceleration, that actually happens at the endpoints because that's when the thing is being swung around the fastest. Okay, so Amax is equal to omega squared times a. All right. And again, these are fairly simple questions. It's more, a lot of this, I mean, mathematically simple, but it's very important that you be able to interpret the questions correctly. Let me see if there's any. Oh, no questions so far. All right, let me continue here. Um, Vectors, before we got to 2D kinematics, I had to teach you about vectors. And vectors, there was conversion from polar to Cartesian and Cartesian to polar. And if you have the polar coordinates, that's r and theta, you obtain x and y from them by those equations right there. Okay, x is equal to r cosine theta and y is equal to r sine theta. And if you have x and y and you want to get the polar, Cartesian to polar, it's r is equal to x squared plus the square root of x squared plus y squared. And theta is equal to the inverse tangent of y component over x. But then you might have to decide, do I add nothing? Do I add 180 or do I add 360? And that depends on your quadrant. If you're in quadrant 1, you add nothing. If you're in quadrant 2 or 3, you add 180. And if you're in quadrant 4, you add 360. Okay? And there's one other thing that I forgot to mention here, and I actually didn't have that in the assignment, but you should know it at this point, okay, for the test. And that is, how do you add vectors? Okay, and so maybe I'll do an example here of how do you add a vector, say, one vector with x is equal to, I don't know, 5, and y is equal to 7, plus another vector x. We'll do it in Cartesian because that's easiest. Negative 3, and I don't know, y is equal to 6. Or let's make it minus 5, like minus 5, like that. Okay, so how do you add vectors when they're in Cartesian? Okay, now if they're in polar, you convert to Cartesian, and you have to do that everywhere because all of the actual machinery of the mathematics is in Cartesian. So polar is more natural, but Cartesian is what you need for any kind of mathematics on vectors. And so I'll do that example there. And then after we had finished vectors, we did constant acceleration, 2D constant acceleration. I didn't do a general theory in 2D. There's no need to. Okay, once you've got it, what it's all about in 1D, it extends fairly easily to 2D. And so in 2D, you've got these first three equations, and these first three equations, you should have these things memorized. Okay, even though it's an open book test, have them memorized in the sense that you know cold what's involved in each one of them. Even if you just write them down and you haven't really made an effort to memorize them, the problem is that at the moment you may get confused about which one to use. If you have them committed to memory, you'll be much faster at knowing which one to use. Okay, but if you take a look at the first three there and you go back to 1D kinematics here like that, you'll notice that the 1D kinematic equations, these three 1D kinematic equations, and these ones are the same. Okay, there is a difference in the names of the variables because we now have two axes, an x-axis and a y-axis. Okay, and we put the y-axis vertically, sorry, the y-axis is vertically, and the x-axis is horizontal, and so as a result, the names have changed, but they're really the same equation. So above we had x is equal to 1/2 a t squared and so on. But here we have y is equal to 1/2 ay t squared plus v naught yt plus y naught. Vy is equal to ayt plus v naught y. And vy squared is equal to v naught y squared plus 2ay y minus y naught. Okay, and then the only x equation is x is equal to v naught x t plus v naught. Okay, sorry, plus x naught, like that. All right, and that was actually last week's stuff. And then we also did uniform circular motion. And here are the equations for uniform circular motion. And I wrote them the way I presented them. But if you look carefully at these equations here, and you look carefully at these equations here, for the harmonic oscillator, you're going to notice that there's some patterns. I didn't write these in terms of omega. I didn't use omega for uniform circular motion. I could have, maybe I should have, but there is an omega there. There's a latent omega inside there. Take a look at what omega is equal to. Omega is equal to 2 pi divided by the period of the motion. Well, just like with oscillation, there's a period. There's a period with respect to uniform circular motion. In fact, simple harmonic oscillation is just uniform circular motion squished. I mean, imagine you have a circle, but instead of worrying about the circle, you just worry about the x projection of the circle, so just squish it down. Well, if you're going like this, here, let me slowly squish the circle, and it becomes an oscillator. Okay, so just look at that 2 pi over capital T. There it is right there, 2 pi over capital T. There's 2 pi squared divided by capital T squared. Okay, so you've actually got an omega in there as well. All right. So these equations are also similar to the equations for the simple harmonic oscillator. And the interpretation here is v is the tangential velocity. That's the velocity as you go around the outside of the circle. It's how fast you're traveling. Since it's uniform circular motion, the word uniform means constant speed around the outside. Okay, and there's acceleration. It's centripetal acceleration. It's towards the center. Okay, so you should know the directions as well. Okay, tangential means along the outside. Centripetal means towards the center of the circle. Okay, towards the center. And this third equation is just the other two equations with the period removed. Okay, or eliminated. All right, let me take a look here in the chat. Okay, I don't see any questions here. So let me open it up to you. Would you do you want to see this problem here say solved? Is that something, or is that too trivial for you guys? Okay, I know there's a 30-second lag, but I'll see here where I highlight. Yeah, okay, so you should have heard my question. So does anyone want to see that or not see that? Okay, not getting any response in the chat there. Well, let's do it then. I mean, I'm not getting anything that's saying not to do it. So or any other questions. So let me go ahead and proceed to do that one. The reason is that that's further into the past, and so you probably need some refresher on how those questions are done. Okay, so let's take a look at this one right here. What do I have? I have remember, this is general kinematics, so I give you x is a function of time. Now, I mean, I could write it like that. That just means that x depends on time. Okay, x is a function of time. And I ask you to find the position, the velocity, and the acceleration at these 3 times. I don't know if we have to do all these 3 times. And what's the average velocity? And I didn't complete the question. What's the average velocity? Here, hold on here. What's the average velocity between t equals 1 and t equals 2 seconds? Okay, and you know what, it's kind of annoying to have to do this for all those. Let's just do it for 1 and 2 seconds. Okay, you could do it for more. I mean, once you get the idea. Let me see here. How many questions will be on the exam? The classic question, how many questions? I'm not exactly sure right now because I'm not done, but it will probably be a little under 30 right now. I'm debating. I've got it mostly written. I'm debating which ones are more appropriate than others. Okay, so you're looking at definitely over 24 and under 30. Okay, so I time these things. They should take you about 1 hour to do the test. I mean, I figure if it takes me 15 minutes to do it, it'll take you 1 hour to do it. But I'm going to give you a full 2 hours, and the reason I do that is just so one, it relieves a little bit of stress, and also in case you have technical problems. Because if you have technical problems, I mean, there's very little I can do at my end, and you can wind up, messing around for a while. So there it is. Um, and you know what, I can tell you better later in the week, and I will. All right. Okay, so let me proceed with this question. So the first question is find x at t equals 1 and t equals 2 seconds. So, I mean, that's as simple as just substituting t equals 1 into that equation there. And so you're going to get 3, 1 cubed, right? The t is now 1, minus 5 times, should put a little times in there like that, times 1 plus 7. Okay, and that one's easy enough. You get 3 minus 5 plus 7 like that. And what's that equal to? I guess that's equal to 5. Okay, so that's where it is at t equals 1 second. At 2 seconds, all right, well, I guess this part isn't going to be the same, but at 2 seconds, you have, instead of 1, you have 2 there, and you have 2 there. So what's this equal to? This is 2 to the, should bring up my calculator. This is 8, so that's 24, and then minus 10 plus 7 like that. And so what's that? 14, it's 21. Okay, so that answers, where is it? At t equals 1 and 2 seconds. Okay, so at 1 second it's at 5-meter mark, and at 2 seconds it's at the it's at 20. I guess if this is in meters, it's at 21 meters. Okay, let me look in the chat here. All right, no questions. Let me continue then. How do you get the velocity? How do you obtain the velocity from the position function? All right, I guess this is the annoying thing about, oh, I lost, something just happened. Let me fix that. There we go. Okay. So the velocity is obtained. Oh no, it happened again. I'm sorry, guys, a bit of technical issues here. I don't understand what's going on. There we go. It's back. So the velocity is obtained from the position by differentiating. Okay. So let me just do that for you over here. So the velocity is dx by dt. All right. And when you take the derivative, remember when you're taking the derivative of a t cubed here, derivative, so there's a 3 which is unchanged, and the derivative of t cubed is 3t squared. So you need to know how to do that. And some of you are taking calculus right now. I did put those in the notes. You don't have to know a lot of them, but basically if you've got a cubed exponent there, that comes out in front, that 3 comes out in front, and the exponent decreases by 1. So you go from t cubed down to t squared. Okay, and then for the other one here, that's going to be minus 5, and the derivative of t is just 1, and the derivative of the plus 7 there is 0. Okay, and so that's it there. That's the equation for the velocity as a function of time. Well, 3 times 3 is 9 t squared minus 5, like that. Okay, and so now if you want the velocity at t equals 1, like that, you just use this equation here, which you obtained by differentiating the previous one, and now wherever you have a t, of course, replace it by a 1, and so what's that going to be? That's going to be 9 minus 5, like that, and 9 minus 5 is 4. Okay, and I guess the units would be meters per second. All right, any questions with that? Differentiate the equation. Yeah, thank you, Emily. I know there's a bit of a lag, but yeah, exactly. Differentiate the equation. So now v is v at t equals 2 there. Same equation, all right, but now it's 2, like that. And so 2 squared is 4. 4 times 9 is 36. Okay, so that 36 is like 2 times 2 to the exponent 2 is 4. And I guess I should put a little multiplication in there. Okay. And so 9 times 4 is 36. Minus 5 is equal to 31, like that. Okay. And how do you get the acceleration as a function of time? Hint, you differentiate again. Just make sure you differentiate the velocity. And it happened again. I've lost guys, I'm so sorry about this. I don't know why I keep losing the screen here. Yeah, this is so weird. And I'm even having difficulties getting it back. I don't understand. Never had this problem before. Let me try something different. All right, I'm going to take my image out. I mean, there's no reason to have my image there, uh, but I think this might be more stable. Okay. Yeah. You should be able to see the screen now. Thank you for that feedback. It happens sometimes, and it just seems to be happening a lot of times right now, and I don't know why. So, well, let me continue here. So you differentiate again, but this time you're differentiating the velocity equation. Okay, maybe I should just put that on its own line here. So the velocity equation here is v is equal to that. Okay, and so you have 9. That's that coefficient right there. And the t squared, when you differentiate the t squared, you get 2t, like that. And then the -5, that's just a constant. When you differentiate that, you get nothing, 0. And that's 18 times t. Okay, and so now if you want the acceleration at t equals 1 second, like that, that's going to be 18 times 1, which is pretty trivial. And a is at t equals 2 seconds is basically going to be 18 times 2, which is 36. Okay. So you'll have a question like that where I'll give you a function, position as a function of time, and I'm going to ask you where is it at those particular times. I'm also going to ask you for the average velocity. And if you remember what the difference is between an average velocity and the instantaneous velocity, these are instantaneous velocities. This is an instantaneous velocity there. I don't know why I put those spaces in there. You don't really need them. And I should probably put in here that a is dv by dt, like that. Okay, so so velocity is obtained by differentiating the position function, and the acceleration is obtained by differentiating the velocity function. And the average velocity, which I can't really do, maybe I'll just type average here, average velocity, like that. Okay, it's going to be a delta x divided by a delta t. Okay, and delta here, it's not quite the same as the d. The d means instantaneous, where you're taking the limit and shrinking things down. The delta means like the actual change over a finite interval. And so if I say what's the average velocity, let me just cut and paste that down here. What's the average velocity between t equals 1 and 2? Well, then you're let's do each on their own line. The delta x is what's x at the later time, so what's x at 2, and x at t equals 2. Whoops, I should add a 2 in there. X at t equals 2 is 21. All right, so that's 21. And actually, let me write it like this: x at t equals 2 seconds minus x at t equals 1 second, like that. And that's going to be 21 minus, what was the other one? 21 minus 5. Okay, which I guess is 16. Okay, and the delta t is just your t equals 2 minus 1. Minus 1. That's 1. Okay, and so then if you put the two together, your delta x was 16, your delta t was 1, and that gives you an average velocity of, during that time interval, of 16. Okay, and I didn't put in the units here, I'm just assuming they're all MKS units. Okay, and so you have an average velocity of 16. If you take a look at the actual velocity, at the velocity, actual, I should have called it instantaneous. The instantaneous velocity was 4 meters per second at t equals 1 and 31. And you could see there that the average is somewhere in the middle. Okay, it's not exactly the average of the two added together, but it's somewhere in the middle. All right. So there you go. Is there any problems with that one? I just thought I'd redo that because that lecture was a bit theoretical, and you know, you say, well, what do you expect? Um, what kind of questions can you expect? This is exactly the kind of question, and it's also the same kind of question that was um, on the assignment. Okay, so I'm not seeing any other questions. I don't want to do a 1D for the reasons I said. I mean, they're kind of trivial. Um, and these ones are kind of trivial too. Let me do one of these. Let me do a vector, okay? And let me do this example one. I probably should have given you one like these on the assignment. They're pretty simple, and I didn't really think about giving you that, but I do expect you to add vectors when they're in Cartesian, and it's super trivial, but still, if you don't know, you don't know, and then you won't get it right. So if you have a vector here, so this is x in Cartesian, x is equal to 5 and y is equal to 7, and you have another vector where x is equal to -3 and y is equal to 5. The resultant vector, actually, I could even put little subscripts on this. Let's call that x1, y1, and x2, y2, like that. Okay, so the x component of the first vector, x1 means x component of the first vector, and y component of the first vector. The resultant x is just going to be the x's added together. Okay, so that's going to be 5 minus 3 here, like that. All right, and that's equal to 2. Okay, so to get the x component out of the two vectors that you're adding, just add the two x components like that. And to add the y component, or to get the resultant y component, just add the y components like that. Okay, and so you get 7 plus -5, and of course that's equal to 2. So the resultant vector is actually at 2, 2. Okay, so uh, very simple, I know, but again, if oh no, it happened again. There's something clearly wrong today. I mean, I'm almost never had this happen. It does, like I said. All right, you should see it in a sec. I'm so sorry. This. Okay. All right, it's back, and let me just repeat what I said. It's straightforward, but let me repeat. And I think what I'll do is I've got a screen here where I can see what you're seeing. I think I'll look at that screen rather than looking at my whiteboard directly. And then if it happens again, which it might, I'll know it right away rather than having to wait for you guys to give me feedback. But thanks for the feedback. So here we had like one vector, which was x1 is equal to 5, y1 is equal to 7. And then we had another vector where the x component, x2 is -3, and the y component, y2 is -5. And to get the resultant x, when you add the two together, it's x1 plus x2. So you just add that 5 to the 3 there. You add the x components to get you the resultant. And to get the resultant y components, you add the y components. Okay. Now, the reason it kind of slipped my mind was because you don't need this for the 2D, but we will need that when we get right after the test when we do forces. So it's good at this point to make sure that you guys know how to add vectors. All right. Okay, so it happened again. Holy mackerel. I got to figure out why it's doing that. All right. Should be back now. Oh, I know why this happens. It happens every time I switch to look at the chat, and it does. And so I wonder if I do this. Here I am solving my technical problems. Well, yep. Okay. Um, well, I mean, that was annoying, but it was worth it because now at least I have an understanding of why this happens sometimes. Because for all the semester, it's done it every once in a while, and I just couldn't figure out why. So, well, okay, there we go. Okay, so I assume there are no questions about that because it's fairly straightforward. And let me see. Let's do a 1D harmonic oscillator problem, and then we'll just leave it at that. The 2D here, we just did it last week, and it's this week's assignment, so you'll have opportunity to ask me. Let's do a 1D harmonic oscillator problem. Okay, so let's say we have example here. Uh, just create this one, e.g. Uh, an oscillator is found to have a period of motion of 2.5 seconds. Okay, um, the okay and the velocity is found to be I don't know, 10 meters per second when it passes through equilibrium. Okay, and so now I can ask a series of questions here. All right, so the first question I'm going to ask is what is maximum velocity? So what is max velocity? All right, now if you know the answer, it seems like I just gave it to you, and I did. But the question expects you to know that when an oscillator passes through equilibrium, that's when the velocity is maximum. And so if I say the velocity is found to be 10 meters per second when it passes through equilibrium, the maximum velocity is 10 meters per second. Okay? All right. What is the amplitude? All right, so what's the amplitude? So the amplitude, A, say you look through the equations here, and of course you don't see an equation that has A equals, but you see this one, the second one, and you go, oh, I know V max, and I know the period, and if I know the period, I know omega, so I know V max and I know omega, and therefore you can calculate A. Okay, so you know, you have to combine a couple of equations here, and so you say, okay, well, first use this one to get omega. All right, and that's going to be 2 times 3.14 divided by 2.5, which is the period right there, 2.5 seconds. All right, and bring up my calculator here and do it very quickly for you. 3 times pi divided by 2.5. And that's what I get, but I'm going to round it off because I'll stick to just 3 significant figures. And the units are hertz or per second. Okay, so all right, now that we have that, next use this one, but we're going to rearrange it. Obviously, I'm going to put some spaces in there. We're going to rearrange it because we want to isolate A, so divide both sides by omega. So you got V max divided by omega like that, and I told you that V max is 10, and that omega is, we just found that, it's 3.77 like that. And so that's going to equal 10 divided by. So that's going to equal this. All right, like that. And let me round that off, okay? And that'll be in meters per second, all right? And then finally, what is the max acceleration? And now, I mean, once you kind of get omega, like everything unravels here, that's how you're going to get the maximum acceleration. So it's going to just be your omega right here, omega squared, like that, multiplied by A, which we've, oh, that's not meters per second. I'm sorry, guys. That should be, that should be meters, right? Because distances are measured in meters. And so that's going to be 3.77 squared multiplied by 2.65. All right, and round that off. and this, whoops, 7, and this is in meters per second squared, like that. All right. So let me see, any questions in the chat? No, it looks okay. So how much time do I have left? Oh, you know what? About we go till 10 after, about 15 more minutes. I can do one more. I'm just sort of doing some spot questions that I think, are things where I didn't emphasize enough during the class. So did that. We did that. Uh, Constant 1D. You know what? The 2D, I changed my mind. The 2D here is a little bit involved because you have to draw a diagram. So let's do a simple 1D, okay? They are simpler than the 2D, but given the time and that we just did 2D constant A, let's do one of these. And let me see, what should we do here? How about I always do things that are falling or throwing things up and down. How about we do, just, oh, look at that. It happened again. Okay, let's just do a car driving. Okay, so a car is driving at let's say 65 kilometers per hour and speeds up to 100 kilometers per hour in should we use a distance? Oh, let's see, over a distance of 100 meters. Okay, and so two questions here. What is the acceleration? All right, and the other question is, how long does it take to accelerate? To speed up. All right, there we go. It's a 1D problem. All right, see here in the chat. All right. Okay, so what is the acceleration? Well, if you look at these equations here, you'll notice that equations 1 and 2 have time in them. All right, and so you can't answer that because you don't know the time. All right, you got to use number 3. All right, so that's one thing. And the other thing is that I gave you the numbers in kilometers per hour, so you really need to change them to meters per second. The initial velocity, I'll do that down here. The initial velocity is 65 kilometers per hour. All right, and rather than showing you the formal way of doing it, the very quick way of converting is just divide by 3.6. And the reason that works is because to convert to kilometers, you're basically dividing by 1,000. And to convert the hours to seconds, you're multiplying by 3,600. 3,600 divided by 1,000 is 3.6. Sorry, I said it the other way around. You multiply by 1,000 and divide by 3,600, so it's like divided by 3.6. And so 65 divided by 3.6 gives you round that off, 18.1 meters per second. Okay, so there's our initial velocity. The final velocity, I've done this one so many times, I know it's 27.8. Let me just check to make sure my memory is right. Yeah, 27.8. Okay, and so the final velocity is 100 kilometers per hour. Okay, and again, just because I said it backwards, let me just re-say it. To change from kilometers to meters, you're multiplying by 1,000. To change from hours to seconds, you're dividing by 3,600. So multiplying by 1,000, dividing by 3,600 is equivalent to just dividing by 3.6. Okay, and that gives you an answer of 27.8 meters per second. All right, like that. Okay, and so now here's the equation we're going to use. All right. And what are we trying to find? Well, the first question, I just kind of covered it up there. The first question is, what is the acceleration? So we're trying to find A. So we have V, we have V naught, we're trying to find A. And you wonder, what is this X minus X naught? Now, I didn't draw a diagram, which is something I always say you should do, okay? But in the diagram, you get to choose where your origin is. And let's choose the origin where the car starts to speed up. And then the distance that it travels is where it finally speeds up. The difference between those two has to be 100 meters because I tell you right here in the problem that it speeds up over a distance of 100 meters. So no matter where you put the origin, that x minus x naught being where, it's at 65 and it just starts to speed up, and that x is where did it finally reach 100, that distance in there has to be 100 meters, okay? And so in substituting here, the v is 27.8 squared, like that, all right? And v naught is 18.1 squared, like that. And then plus 2 times, we're looking for the acceleration, and the x minus x naught is the distance over which it sped up, and that's 100, like that. And here, I'll do it one step at a time here. So 27.8 squared is 700, and I'll keep an extra digit just in case. And then 18.1 squared plus 200. That's 2 times 100, and then there's an a there, like that. Okay, and let me see what this works out to. 771.6. Whoops. 0.6 minus, and then divide that by 200, and I'm getting an a value of that. Okay, so I'm getting an acceleration of 2.22 meters per second. Now ask yourself, does this acceleration make sense? Okay, what's a good acceleration to compare a number to? Like, what would you compare this to say is this reasonable? All right, well, I'll go on and you can answer that. So how long does it take to speed up? And now you can take a look at these equations. You can actually use either equation number 1 or number 2. Number 1 is a quadratic y. Just use number 2, obviously, right? And so, because now we know a. And so if you use number 2 here to get the time, like this. So v is, that's the final velocity, is 27.8, is equal to 2.22 t plus the initial velocity was 18.1, and that gives you a t of, work that out. So you take, whoops, I forgot to put a plus in there. So you take 27.8 minus 18.1. Okay, and then divide that by 2.22, and I find that that is about, oh, I missed the 4 point. There we go, 4 point, is that right? Yep, 4 point blah, 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 and then we'll just round that off to 47, like that, seconds. Okay, so that answers that question. All right. Now, I didn't draw the diagram, and you know what? It doesn't take too long. As I'm speaking, this other program should come up, and I do want to show you what the diagram should look like. But in the meantime, let me just look here in the chat. Okay, well, no one answered the question, what's a good acceleration to compare this to? When you're talking about accelerations that you would experience like in the real world, the number to always compare it to is, what do you think? 9.8 meters per second squared. Okay, so compare to 9.8 meters per second squared, which is the acceleration due to gravity. Think about the question, like try to picture physically what I'm describing here. I know sometimes you get lost in the math and everything, but you're driving a car. okay, and you're traveling at 65 kilometers per hour. Okay, now you may not know what 65 kilometers per hour is, but it's like 40 miles an hour, roughly speaking. And you speed up to 100 kilometers per hour. And again, living on this side of the border, if you were in Canada, you'd know that that's highway speed. Here it'd be like 55. So you're speeding up from like 40 to 55, and you're doing it over a distance of 100 meters or about 300 feet. Okay. You don't expect the acceleration to be more than your acceleration due to gravity. That would be like your entire weight of your body being squished back into the car. Okay, and so yeah, that would be like way too much. If you got an answer which was bigger than 10, I mean that would be like I mean that'd be like a rocket ship, or not maybe a rocket ship, but a plane, a jet or something speeding up. Then yeah, you might get your whole weight being pulled back into your seat, but not if you're driving a car. So you compare 2.22 to 9.8, and yeah, it's a significant acceleration. You would feel it, okay, but it's not that much, okay. And then the other question is, well, how long do you expect this to take? And you get like 4 seconds, okay? So then that seems reasonable as well, okay? Let me see here if there's any questions in the chat. Nope, no questions. And also, it seems that all the other technical stuff is good. And again, thanks for the feedback, because I could go on a long time without noticing a problem at my end. All right, so let me just show you how you would draw this picture. And so I'm going to switch here to yet another screen like that. And there you go. You should see my whiteboard. And so I know we solved the problem already, but it's worth looking at how you would do this. And so step number one is you just draw a picture of what you would see, which is a road. Here's my car initially. And really you're trying to draw a movie. And you can't draw a movie because you're trying to draw the car dynamically changing over time. But there's the car initially, and there's the car after it has already sped up. Okay, and so this is what you would see. And I guess in here you would see speeding up. I don't know how I would draw that, but maybe something like that. Okay, so there's the car speeding up. All right, now the next thing you do is you add a coordinate system, and I'll do that in blue as I usually do, as I've done in the past. And that basically means, it's 1D, so, you need a ruler. Okay, so there's your plus X like that. And rulers have a 0. So you say, where do you want to put the 0? Right there. This is where the car first starts to speed up. Okay, so there's your x naught is equal to 0. All right, and then this is where the car has finally sped up to 100 kilometers per hour. And so what's that? Well, the question says that it takes that this whole distance in here, that whole distance has to be 100 meters. So there, that's 100 meters. Okay, and then you say, well, how fast is it going initially? Right here, that's the initial velocity, and I told you that that was 65 kilometers per hour, like that. Okay, and then it speeds up to, and I tell you that it speeds up to 100 kilometers per hour. I know you have to convert it, but just, taking the raw numbers, like that. Okay, and that's it. That's all I give you. Okay, and so that's the diagram for that particular problem. Okay, t t equals 0 is here. Maybe I can put t in there just to be very clear. Okay, but the t over here, when you finally have sped up, I didn't tell you what that was. Okay, and the a, you are accelerating here, you're speeding up, but I also don't tell you what that is. Okay, and so when you go to do the problem, you have the initial position. I mean, circle in red. Initial position. Oh, red. Initial position. You have a final position. You have an initial velocity. You have a final velocity. You have an acceleration or an unknown acceleration and a time like that. Okay. So there it is. Same steps in 2D, like literally the same steps, but now expanded to the general case of having to look at both X and Y directions. All right, so just a brief summary about what's on the test there, and let me switch back to this one right there, and um, we're done, but let me just go over it again. In case you missed anything the first time. So measurements and unit conversions, a general 1D kinematic. And here I did do a problem like you will see on the test. It'll be just like that. And that's just like on the assignment. You will have a problem in 1D acceleration constant, but they're fairly straightforward. Okay, I think you would agree that now that you've done 2D, okay, we did one of those. And harmonic oscillator problem. Okay, and those are the equations. We did one of those. And uh, a vector problem. I didn't do the conversions, but like I literally think everyone got like perfect on that assignment. I mean, it really is quite easy. I didn't show you an addition one, but we did one of those. Okay, and we didn't do the last two. Okay, so I didn't do an example of the last two. Constant acceleration 2D. They're quite involved, and hopefully you were with us for the live stream on Friday when I went over that. Uniform circular motion, I didn't do that, but they're fairly straightforward too. And both of those were last week's topic. Okay, I'm just going to hang out for a little bit longer to see if there's any questions. I'll even ask here in the chat any questions, concerns, objections, whatever. If not, we're done. Okay, so let me just switch back to this. And I know you're not seeing the background, but uh, let me just say goodbye for now. And I apologize, but next Wednesday I won't be around for this hour, but I will be around during the day. We can do another live stream if you want to see more examples, or in the evenings, every evening, and I'm sure even Wednesday evening and Thursday evening, I'll be available for our usual Google Hangouts. Okay, so if there's nothing else, we'll just end the stream. Not seeing anyone saying anything in the chat. All right then. Bye bye.